Hello everybody, welcome back to another Engineering Statics lecture video. Before we begin, I just want to say I hope you guys are all doing well, still nice and happy, and hopefully you stay that way, because if we're getting to this topic, it usually means that the midterm is starting to approach pretty fast, so hopefully you guys are buckled down and ready to study, basically. Now, I have to give a little disclaimer before we start this video. This one could be a little bit longer. The problem is to end this week, we have two major topics. And these two topics I would usually split into two separate videos because, again, they're big topics. But these two are so intertwined with each other that I've decided to leave them into one video so that when I mention one topic, you guys will automatically think about the other topic and vice versa. It's going to be the secret to your exam question. So with that being said, I suggest before you start this video, maybe grab some popcorn, grab a drink, get cozy, stuff like that, because I'm not sure how long this is going to be, but it could be a little bit longer. Now, if you guys are coming for a specific section, maybe just something like cross product, of course I have the video split into chapters so you guys can fast forward however you like. Alright, so again, get comfy. Once you're comfy, we will begin. So this entire video is dedicated to one topic, and it sounds very simple. It's moments in 3 dimensions. Remember, the last video we talked about moments in 2 dimensions, and we basically said, oh, it's a piece of cake. We just take our force, multiply it by a perpendicular distance, we're good to go. Well, as you guys are going to see, moments in 3D, well, kind of blows chunks. And the reason why is because in 3D, it's very difficult to get that perpendicular distance. So what we're going to actually have to do is use position vectors if we want to go to that route. So let's say I have a nice 3-dimensional space and I have my force vector F. Now, again, moments are specific about points. Depending on where you take the moment, it's going to be different. So let's say in this particular case, I want to take the moment about point O. Now again, to get this moment, I basically have to find the perpendicular distance between my force vector and that point. So I'm going to look for this distance right here, and the question really becomes, how do we find that distance? Well, again, as I kind of hinted to, we can actually use position vectors if we want. So we're going to break this down into a series of steps. The first one, of course, is we need to define a point along the line of action of the force vector, right? So that's going to be the first step. So let me go to the ass of the vector, and I'm going to define a point right there. From there, I can actually create a position vector from the point I want to take the moment about to the point on my force vector. So it would look something like this. So it goes from the point where I want to take the moment about over to my force vector. From there, we talked about the thing called dot product. And dot product allows us to solve for angles between two vectors. So if I wanted to, if I have my force vector and my position vector, I can figure out that angle theta between them. Now note on the other side, that perpendicular distance d, it's perpendicular to f. So we actually just formed a right triangle. So the first thing to do would be to solve for that angle, and we have a nice formula with the dot product where cosine of theta is equal to my force vector dotted with my position vector and then divided by both magnitudes. And again, since we created a nice right triangle, we can actually use just simple trigonometry to solve for that perpendicular distance, where the perpendicular distance is going to be the magnitude of that position vector multiplied by sine theta. Now you guys may be saying, that sucked. And I agree, that sucks. So no one wants to do it this way. It's a lot of work, it's inconvenient, but more importantly, think of the result. At the end, we have a force times a distance, so we're going to just get a number, let's say 100. That 100 doesn't tell us anything. In 2 dimensions, it was nice because all of our components, if we're in the xy plane, all of our moments are about the z-axis. Every single one of them, no matter what we're doing if we're in 2 dimensions. In 3 dimensions, we get a number if we do it this way, but we don't know if it's about the x-axis, the y-axis, the z-axis, or anything about it. So what we actually have to do is find a better way to determine moments where we can figure out moment components, so that when I get my moment, I know the moment about the x-axis, I know the moment about the y-axis, and I know the moment about the z-axis. So this is where something called the cross product comes into play. So again, this video is 2 large concepts, that being 3D moments, and the second one is cross product. So this is why it could get a bit long, but again, they're intertwined. I want you guys to always think of 3D moments and cross product together. And the reason why is because in an exam, I promise you guys, all right? I promise you this is the Clayton guarantee. You guys will get a question about moments in 3D. And I want the first thing you guys to think about is cross product, all right? Cross product is what's going to save you in this particular scenario. Now you guys say, all right, Clayton, cross product, 3D moments looking pretty good. But what the hell is the cross product? Well, the cross product is defined as a vector A crossed by a vector B, and the result is another vector. So there's going to be the first key thing here. The result is another vector. When you guys think of dot product, we took two vectors and we got a scalar. In the cross product, we take two vectors and we're getting another vector. But what exactly is this vector? Well, it's going to be called vector C, and it's again simply denoted as vector A cross with vector B. It looks like a times sign, and you guys can probably use a times sign. Everyone will know what exactly you're doing. Now, this resultant vector C has some very specific properties, which we're going to discuss right here. The first one is this. Let's say that vector A and vector B are in the XY plane. Now you guys are saying, Clayton, why are you doing that? Well, it's going to become apparent really really quickly, I guess. So the first thing is, if I were to take vector A and cross it with vector B, the resultant vector C is going to be perpendicular to both A and B. So your resultant vector, no matter what it is, a force vector, position vector, anything you want, it's always going to be perpendicular to the two input vectors. So in this particular case right here, if I cross A with B, I'm going to get a vector perpendicular to both. This is why I had A and B in the XY plane, because now I can say that my resultant vector, A cross B, it's actually going to be in the Z direction, all right, and it's going downwards. So another thing is the direction of C follows the right-hand rule. So again, you guys may be looking at that and say, Clayton, why is it going downwards and not upwards? Well, this cross product follows the right-hand rule. So if I want to determine the direction of that vector, what I actually have to do is I have to go from A to B. So in this particular case, I go from A, I curl over to B, and as you can see, my finger is pointing downwards. Now, this is actually very important, and it leads to the next property where, I guess not quite the next property yet, but the next property we're going to talk about is the magnitude of this resultant is actually equal to the area formed by vector A and vector B. Now, this isn't something you guys are going to know or something that you guys are really going to utilize, but it's going to make the proof that we present on the next page rather simple. So if we have vector A and vector B together and we cross them to get vector C, well, the magnitude of C is actually going to be equal to the area of this parallelogram formed by A and B. Again, not something that we really use here in engineering statics, but it's going to be important when I show you guys the proof, at least to help it make more sense to you guys. Now, I got ahead of myself, and the other property I want to talk about was this. Since the cross product follows the right-hand rule, it's very important the order of the vectors. So the cross product is not commutative. I don't really know how to say that correctly. I'm going to be honest. Maybe you guys can correct me in the comments. But basically what this means is A cross B is not equal to B cross A. All right, so this is the one thing I really want you guys to remember. A cross B is not equal to B cross A. And again, it's because of the right-hand rule. If A is over here and B is this way, well, if I go from A to B, I'm curling. As we can see, my thumb is downwards. So it means that the vector is pointing downwards, as we see in this example. Now, if I were to go from B over to A, I curl the opposite direction. In this case, my thumb is pointing upwards, so the vector, if I were to go B cross A, is actually going to be pointing upwards. Now, the vectors B cross A and A cross B, they're going to have the exact same components. They're just going to be in the opposite direction, okay? So that's what's going to happen. If you guys accidentally take the wrong vectors or do the order wrong, the components are going to stay the same, but all the components will have the opposite sign of what they should actually have. So we can also do some fun things with the cross product, including scalar multiplication, as well as distribute it with some vector addition. I'm not going to talk about those too much because I'm going to be honest with you guys. I'm not the kind of guy that likes to show you all this fancy stuff and say, oh, you need to know it. I've never seen a case where you guys actually need to know this stuff. I'm just going to put it on there so you guys know, can be aware of it. But again, I've never seen it where you have to use it in this particular course. If there's one thing I want you guys to take away from this slide, it is this. A cross B is not equal to B cross A. The order of the cross product is going to be very important. Now you guys may be saying, Clayton, we just talked about the cross product a lot, but you still haven't showed us how to calculate the damn thing. So let's go to the next slide and figure out how exactly do we calculate the cross product to get that resultant vector C. Well, it's actually very nice and ugly at the same time. So the best way to show you guys the calculation is to show you guys the proof. So let's say that we have two vectors. We have vector A and vector B. And again, as you guys may guess, the goal is to cross them together to get vector C. So C is going to be equal to A cross B. Now, just like the dot product before, we're going to kind of take everything and multiply everything, and we get this big ugly thing right here. Now, in dot product, we would have I dot I, and we can say that that's equal to something. But in this particular case, we get a bunch of vectors cross each other. So I got I cross I got I cross J, etc., etc. Now, just like the dot product, we are going to solve this by figuring out what exactly each one of those things means. And this is why I listed some specific properties on the previous page. So let's go to 3D vector space where we have our x, y, and z. And one property which I kind of mentioned before in the dot product, and I'm going to mention it again here, but it's not something you need to know, is that I, j, and k, where we use in our Cartesian vector notation, they're actually vectors, where I is equal to 1, 0, 0, j is equal to 0, 1, 0, and k is equal to 0, 0, 1. All right, they're actually vectors. And we can use those properties that we talked about on the previous page to make some nice simplifications. The first one is this: anything cross itself is going to be equal to 0. And this is why I told you that identity, that the resultant vector is actually the area of the parallelogram formed by two vectors. If the two vectors are the exact same, just like this, well, they create no area. So that's one of the reasons why I showed you guys, so that when it comes to this particular proof, you guys are saying, oh, okay, I understand why a vector across itself is actually equal to 0. Now, this doesn't do too much, but in our equation above, we can now cancel out three specific terms. You guys are saying, all right, I see where this is going. It's going to cancel out, and it's going to look pretty sexy. Well, not quite. It's going to look pretty sexy, but not a lot of things cancel out. In fact, these are the only things that cancel out. The rest just kind of simplify, but they don't cancel out. So the next thing is this. If we were to go around in a circle, and by a circle I mean I, J, K, that very specific order, I, J, K, I, J, K, I, J, K, that order matters. If we were to cross two vectors, we get the third one. So if I take I and cross it with J, I get K. And this is the property that if I were to cross two vectors together, the resultant vector is going to be perpendicular to both of them. So if I cross the x-axis with the y-axis, we know that the vector perpendicular to both of those axes is going to be the z-axis. That's why I got I cross J is equal to K. And I can keep going in this order and say that J cross K is equal to I, and K cross I is equal to J. Now, this appears 3 times in our equation, so we're going to keep this in mind right here, and we're going to substitute it in a little bit later. Now, when I talked about this one, I said that the order is important. I, J, K, I, J, K, I, J, K. Now, if we were to go the opposite way and go K, J, I, K, J, I, we get this following thing, where J cross I is equal to negative K. It's the same reason as before, where the vector is going to be perpendicular, but the order of the vector matters because of the right-hand rule. So in the first case, we would go something like this, where it's pointed upwards, but in this case, we're going the opposite way, which is why it's simply going to be negative. So this also appears 3 times. So again, we can't cancel anything out, but we can actually simplify it into the following, where C, which is equal to A cross B, is equal to the following. And as we can see, it's a vector with 3 components. Now, this goes back to what I said. When we do the cross product, our result is actually going to be a vector. It's not going to be a scalar like dot product. It's going to be a vector. And of course, it has 3 components. Now, you guys are looking at this and saying, Clayton, this is ass. And I agree. This right here is not fun to memorize. I have a little trick, which I'm going to show you guys in the next slide, how I memorize it. But for those of you at the University of Alberta, do not worry. Typically, we give this on the formula sheet. So if you guys forget exactly this formula, go to the formula sheet. It'll show you guys how to do a cross product. Now again, when I mention cross product, I want you guys to always remember 3D vectors. We haven't really talked about it yet, but cross product is heavily related to 3D vectors. And you guys are saying, okay, Clayton, if this is related to 3D vectors and it's a formula that's given on my formula sheet, everything's looking pretty good. Yes and no. There's one sneaky bitch that you guys always have to remember. 9 times out of 10 when students make a mistake using cross product, it's this right here. As we can see, we have an I component and then we have a j component, but keep in mind that we have a negative sign in front of that j component. Students will always forget that negative sign. I promise you, always forget that negative sign, and then they get their j component wrong. So when you guys are using this formula, keep in mind that there is a negative sign outside of that j component. If we look at the k component, it's still plus, but that j component has a negative sign. Please don't forget that. Now you guys may be saying, Clayton, I don't want to have to rely on a formula sheet, and I don't blame you. I hate formula sheets too. How can I memorize this formula? Well, I use something called the fish method. And the fish method is based on the idea that the cross product is simply the determinant of a matrix. Specifically, this matrix right here, where the first row is ijk, which we know. The second row is the components of vector A, and the third row is the components of vector B. Now, a lot of you guys are first years and may or may not have taken linear algebra. If you guys have taken linear algebra, you guys are laughing, saying, Clayton, I know the cross product. I know exactly what a determinant is. I'm doing pretty good, and that's great, so I'm happy for you. But unfortunately, a lot of first years don't take linear algebra before this course. So in this case, you guys may not know what a determinant is, and that's okay. I'm not going to teach you what a determinant is. It's something you guys can explore later. It might make you a little bit sad because it's just gross math. But we can actually write this in a very specific way. Now what I'm going to do is I'm going to write it like this because this is how I'm going to show you guys my own little fish method. Now you guys are saying fish method, this sounds like a joke. Well, yes, it's kind of a joke. It's a trolley method, but it works, right? Trolley method, but it works. So writing the cross product in this specific way where I have it as basically 3 rows and 3 columns allows me to use my fish method. Now it has some specific steps. So if I want to take A and cross it with B, I'm going to follow these steps. The first one is I'm going to cross out the column of interest. And by that I mean this. C is a vector. It's going to have 3 components. It's going to have an I, a j, and a k. So if I'm interested in the I component, I am going to cross out that I column. All right, so that's going to be my first step. The second step is I'm going to draw a fish on the uncrossed values. All right, I'm going to draw a fish on the uncrossed values. And now this is when you guys are saying Clayton's losing his mind. What does he mean? Well, if I cross out AX and BX, my uncrossed values are simply AY, AZ, BY, and BZ. And I'm going to draw a fish. So it's going to look something like this. And don't judge me, this was the best I can do in PowerPoint drawing a fish, but it's going to look something like this. Now, I can determine the calculation of that component based on the path of the fish. Fish. So that should say fish. I'm going to correct that before I give you guys the notes. But it's based on the path of the fish. So notice how I don't have the formulas on screen yet. But if I were to go through the fish, I start at AY in the top left, and I go down to BZ. So we're going to go AY times BZ. Now when I flip up, I'm going to have the negative sign. So we're going to go AY times BZ minus AZ times BY. And if I were to look at my formula, that's exactly what we have. So again, we're just drawing a fish. AY times BZ minus AZ times BY. And that's going to be my I component. After we find the I component, we simply repeat this method for the other components. So we're saying, all right, we got I, we're looking good. How about J? Well, again, if I'm interested in J, I'm going to cross out that J column, and I'm going to look at the uncrossed values. From there, I'm simply going to draw my fish and trace the path of the fish. So, of course, we go AX down to BZ, so AX times BZ minus AZ times BX. Again, I just drew a fish, and that's going to be my J component. Again, AX times BZ minus AZ times BX. And then finally, I can repeat this for the K column, where I'm going to draw my fish. I go AX times BY minus AY times BX. So if you guys start to remember the fish method, it's pretty easy, and it's a little bit controversial because a lot of the students in my class, including myself, we call it the Jesus fish. Because if you guys look on like those bumper stickers, those Jesus fish, I don't know exactly what they're called, but that's what they look like. And the reason why I say that is this. I'm not trying to start a controversy. I find that if I were to say something that may start a controversy like that, you guys will always remember it. You guys were thinking fish method, I'll probably forget. But now that I mention that, you guys will never forget the fish method. I guarantee it. And the reason why I can say that is because it was on my reviews as a professor last year. What was the most memorable thing about the course? Everyone said the fish method. Probably because of that. So that's it. Now, if we look here, this is a very nice method. It allows us to calculate everything we want. Again, one trick. Don't forget the negative sign on that J component. That will get 9 out of 10 students on a midterm, and I feel so bad because I got to dock some marks, and then they get upset with me, and I don't want you guys to be upset with me. I want you guys to all be happy. So again, please don't forget that negative sign. All right, so that's going to be the cross product. And again, I said the cross product is related to moments in 3D. So let's discuss how exactly that happens. So if I want a moment about a point in 3D, I can actually determine it using cross product, where the moment is going to be equal to my position vector crossed with my force vector. All right, position vector crossed with force vector. And remember that order. Remember, we discussed that the cross product is order dependent. If I were to take my force vector and cross it with my position vector, I'm going to get all the components correctly, but all the signs are going to be swapped. So it's important to know that the position vector goes first and then the force vector. So if I were to have a force in 3D and I want to figure out what moment this force creates about point O, all I need to do is create a position vector from the point at which I'm interested in, so point O, to any point on the force vector. So there's the first real trick. It can be any point on this force vector or the force vector line of action. So just for fun, let's say I'm going to the ass of the force vector. I have a position vector now, which goes from point O to my force vector. I have my force vector, so I have my two vectors. All I need to do to find the moment is just cross them together. So the resultant moment is also going to be a vector, which we discussed. And you guys are going to say, Clayton, hold on a second. Why is this moment a vector? So let's see. I cross them together, I get my moment vector. And usually for these moment vectors, we draw a little kind of swirl around them to show that they're not a force vector, they're actually a moment vector. And what's going to happen is it's going to have two components. So I'm kind of getting ahead of myself again. Again, order is important. R cross F is not equal to F cross R. Make sure the position vector always goes first. But again, I want to go to the point, what exactly does this moment vector mean? Well, the best way to show you guys is an example. So let's say at this point I have my position vector. You guys are experts on finding those. And I have my force vector. Again, you guys are experts at finding those. And I want to find the moment about point O. I can use my fish method. I can use some other method. I know that one of the other instructors, Dr. Carlos Cruz, he does his own little weird, I don't even know what to call it. It looks like a dinosaur was clawing at it. But there's that method, whatever method you guys feel comfortable with, and you guys can find the moment as a vector. Now this goes back to what I'm saying is, why is this moment a vector? What are these three components? Well, each one of these components is the moment about that specific axis. So this 25i, this means that the moment around the x-axis is 25. For the y-axis, it's going to be the 90j. And for the z-axis, of course, it's going to be that negative 80. All right, so here's the key here. The moment's going to have three components. Each one of the components is the moment about a specific axis. Notice in that very first method I showed you guys at the very beginning of this video, we didn't really have moment components. We were just given a random number. So it actually gave us no information. The cross product here gives us all the information we need. Now, notice that for that k component, it turned out to be negative. So that's one very sexy thing for us, is that the cross product also takes into account the directions. We don't actually have to try and manually include any directions. The cross product takes care of that for us. So again, I just want to say it one last time so you guys know. Moments in 3D, cross product. Moments in 3D, cross product. If you guys know that, you guys will be absolutely fine in your midterm or final question. Again, the only trick, make sure the position vector is before the force vector when we cross them. Order is very important. So now you guys are saying, all right, feeling good. Maybe you guys getting a little too cocky and you guys are saying, you know what, Clayton, this is easy. Cross product, piece of cake, got a formula sheet, I'm happy. What could they do that would screw me over? Well, that's going to be this. Moments about an axis. Now you guys are saying, Clayton, we have the components X, Y, Z. I'm good to go. And I'm not talking about the X, Y, Z axis. I'm talking about any random axis. Typically what they love to do in an exam is give you a drawing with a door hinge, and the door hinge will be in some random direction, and they'll say give me the moment about that axis. So we got to figure out how exactly do we do that. So let's say that we have our nice 3D vector space, we have our force, and I say, you know what, I want the moment this force creates about point O. You guys are saying, Clayton, you're joking, right? This is a piece of cake. All I need to do is create a position vector from that point to anywhere on my force. I cross them together and I get my moment vector. So it's going to have mxi, myj, and mz times k. And again, we talked about how mx, that's going to be the component in the x-axis. My is the component along the y-axis. And mz is going to be the moment around the z-axis. So you guys are feeling great. You guys are saying this is easy. And then they hit you with this. All right, you know those three moment components. What about the moment component about this axis? And this is where students start to go, uh-oh, because they forget. But this is actually going to be the same type of problem that we faced before in force vectors with projections. Remember, we talked about projections and say that they can ask for the force component in any random direction. Well, we are actually going to use the exact same procedure here. Same as projections. So recall that from before, we can use dot product to find the component of a vector in an arbitrary direction. So if I want the moment about a particular axis, it sounds really scary, but all I have to do is take my moment vector and dot it with the unit vector that is defining that axis. There's only one trick that you guys need to know. If we have the moment vector about point O, we have to make sure that point O is on the axis we want. Let's say that they give us the axis to the side and our point O is over here. Well, we actually can't project it anymore. We have to make sure that the moment we took, or the point we took the moment about, is on the axis that we're interested in. So another thing to keep in mind is we're using dot product now. All right, remember dot product gives us a scalar. We take two vectors, we get a scalar. And this makes sense because the moment about a specific axis should just be one number. Think about the force vector. We have three components, but if I were to say what is the force along the x-axis, well, we know it's just going to be a single number. The same thing applies here. So we dot them together, we get our nice scalar, which is going to be the moment about that particular axis. Now again, I really want to emphasize this. In order for this to work, point O, which we know the moment for, it has to be on that axis. Generally, it always is. If it's not, it's too much work for exams, so professors usually shy away from doing that because they don't want to mark extra things. One secret that you guys may not know, professors are lazy. We typically always make questions so that they're easy to mark. Because if they're long to mark, well, that goes into our time, and we don't want to do that. We'd rather be playing games or watching TV, something like that. So it's very rare where point O won't be on the axis, but it's something just to keep in mind. Now, and you guys may be wondering, the reason why is we don't create a triangle. You guys can look at the projection video to see what exactly I mean by that. So now, if you guys are feeling particularly ballsy and you guys don't want to do these steps. So if I were to look at this question, there's two steps. Find the moment about point O, take the projection. But some of you guys may be feeling really great, you know, big dick energy, and you guys are saying, you know what, I'm going to do it all one step, no problem at all. Well, you guys can do that using something called the triple scalar product. And it's going to be the exact same calculations that we did before using the fish method, but instead of I, J, K at the top, we substitute them with the three components of our unit vector that is defined by that axis. So again, same thing as before, just switch out I, J, K with that particular thing, you'll be good to go. But again, it's ballsy, and the reason why I don't like it and the reason why I'm kind of talking down on it is this. Part marks. I've said it a million times in exams, you guys want to go for those part marks. Those will save your life. If you guys try this all in one calculation and get it wrong, well then there's no part marks. If you guys were to try and find the moment first and then this, well, chances are you might be able to get part marks on both. Maybe you get the moment right and it's just this part that's wrong. So you get all the marks for the moment, stuff like that. So it's kind of one of those high risk, high rewards. If you try and do things fast, a little too fast, and skip things, well, you might be digging a hole for yourself if you get the wrong answer. So I just want to clarify that. I recommend doing it in 2 steps. So again, you guys can take advantage of those part marks if you can. So the final thing we're going to talk about, and this isn't something that we usually find in this particular class because it's a first-year class. We're here to have fun, not make you guys depressed. And that is this: moments in equilibrium. So remember, in 2D moments, we said that taking the summation of moments adds a 3rd equilibrium equation. Well, in 3D, it actually adds 3 more equilibrium equations. So for 3D equilibrium, we actually have 6 equations now. The summation of forces in each direction, so I, J, K, or X, Y, Z, they must all be equal to 0. But the summation of moments around every axis, so X-axis, Y-axis, and the Z-axis, they must also be equal to 0. So this actually allows us to solve for 6 equations with 6 unknowns. So again, we can solve for 6 unknowns with this bad boy. The reason why we don't see it is because solving for 6 unknowns, it's absolutely gross. It's complete ass. No one wants to do it. No one wants to mark it, so even the profs are scared of it. But it's just basically a one-way ticket to make students hate you, which I'm kind of against. I don't want students to hate professors. They should like them. It should be fun. It should be a learning experience for both of you guys. So again, it's something to be aware of. Very rarely will you guys see this happen because, again, it's just a one-way ticket to making everybody hate everybody. So you usually don't see this. But if you guys were doing this and you guys were talking about resultant moments, because again, we're talking about the summation of moments, the question becomes, how do we get resultant moments in a system? And this is something that you guys could be asked just to find a resultant moment. Not solve unknowns, but just find a resultant moment. Well, it's actually very simple using a very specific theorem called Varignon's theorem. I'm not sure if I say that correctly, but the theorem states that the resultant moment about a point is equal to the sum of the moments of the force components about the same point. And this is where I lost you guys. You guys think, Clayton, I don't really know what this means. Well, it's actually very simple. This statement right here basically says that if we have 2 different moment vectors and we want the resultant, we can just add them together, just like force vectors. Remember, force vectors, if we had 3 different force vectors, we wanted the resultant, just add the components together. The exact same thing for moments. So if I had 2 moment vectors, M1 and M2, and they're about the same point. So here's the key here. They have to be about the same point. All I need to do to find the resultant moments, adding them together, is just add the components. So I see that I have negative 2i and I have 4i. So I add them together. I see that I have 6j, negative 1j, just add them together, and I get my resultant moment. Now the key here, and this is what's going to kind of get us ready for next video, is the key here is that both of these moments that I added together, they were about the exact same point. They're both about point O. In the next video, we're going to discuss kind of the final topic before we get to the midterm, and that is the idea that what happens if I have 2 different moments, a moment about point 1 and a moment about point 2. Or let's say that I have 2 different forces, a force about point 1, a force about point 2, so they're on separate sides. How can we get the resultant moments in cases like that? So that's going to be its own separate topic, which we're going to be going over next video. Again, the whole goal of this video is 2 things. Dot product, don't listen to me. Cross product and moments in 3D. Again, make them nice and intertwined in your brain, because if you guys ever are asked for a moment in 3D, cross product. All right? You guys ever using cross product, it should be for moments in 3D. And we discussed how we did that, and that's the goal of this video. So if I give you guys a force vector and a position vector, and I ask for the moment, you guys will be good to go, then this video works. So that's it for this video. With that being said, that's the end of this video. I want to thank you guys so much for watching. I really appreciate it. Yep, it's a longer video. I'm looking at the time right now, so I just want to apologize if I put you guys to sleep. Again, I really wanted to put these 2 topics together so everybody's happy and knows what's going on. So again, thank you guys so much for listening. I really appreciate it. I will see you guys in the next lecture video.